Hi, welcome to the Piezo-Metrics channel. I'm Frank and I'm here to talk about how to install semiconductor strain gauges. Installing semiconductor strain gauges has its own unique set of challenges when compared to installing metal foil gauges. The challenges mainly come from their small size and fragility. To help users of Piezo-Metrics strain gauges, a technical note was written to explain what equipment is needed, what steps are needed for surface preparation, how to prepare a strain gauge, how to place a gauge, and how to solder the gauge's gold wires. A link to the tech note is given below. There's an art to installing a strain gauge. Not everything can be quantified and written into a tech note. This video covers a few things that I believe are easier seen than read about. The techniques I will show come from conversations with the gauging technicians at Piezo-Metrics. Even though I may understand what they do, it does not mean that I can actually do it myself. The gauging technicians are the best at what they do. I chose 3 installation steps for this video because it's difficult to describe them in a tech note. So first, we'll go over how to shape a strain gauge. Second, we'll cover how to place the strain gauge. And third, we'll look at how to solder the gold wires. Okay, so what do I mean by shape a strain gauge? Unlike an encapsulated metal foil gauge that naturally lies flat on a gauging surface, a semiconductor strain gauge will move, flop over, and generally be uncooperative in staying where you want it. There's a higher chance that it will not be where you want it than where you want it. To give ourselves a chance of success, we need to shape the gold wires so they will help the gauge stay where we put it. The basic idea is to straighten out the gold wires and bend them so that they are perpendicular to the gauge's surface. That way, when the gauge is put in the desired position, the weight of the gold wires will press the gauge into the adhesive and keep it flat on the structure's surface. To shape the gold wires, we need a set of tweezers where the tips are aligned and will close without gaps. The gold wires are only 50 micron in diameter. Any gaps will be apparent because it will be difficult to grab the wire. I'll be using 2 tweezers from Excelta. One is a 3C-SA and the other is a 7-SA. Details of these tweezers are given in the description below. The other thing I will be using is a glass plate to do the shaping. Having a hard, smooth surface prevents the gold wires from getting caught on the surface of the shaping plate. I'll show how the gold wires are shaped in the next sequence. The video is taken from a trinocular microscope. My field of view from the microscope is 20 millimeters in diameter. The camera's field of view, which you will see, is 15 by 8 millimeters. I will shape this 1.52 millimeter long bar gauge by first straightening its gold wires. To begin, I'll grab one end of the gold wire with one pair of tweezers, and then grab the other end with another pair of tweezers. Next, I'll pull gently on the 2 wires. If you look carefully, you'll see some of the creases in the gold wires straighten out. If that happens, you've pulled enough. When finished, the wires should be perfectly straight. Next, I'll grab a wedge bond and then tap on the gold wire so that it lies in the same plane as the gauge. If done correctly, the gauge will lie flat on its back. At this point, the wires can be shortened using a razor blade. The wires should be long enough to create a small strain loop between the gauge and the solder terminal. The next step is to bend the wires so that they are perpendicular to the gauge's surface. To do that, I'll grab the wedge bond and hold the gauge so that it sits 90 degrees to the glass plate. Then I nudge the wire near the wedge bond so that it arrives at a 90-degree angle to the gauge. I'll also make sure the wire lies parallel to the glass plate. If the wires don't lie parallel to the glass plate, the gauge will tip over when it's placed on the sensing structure for bonding. Now that the gauge is shaped, the first step in placing the strain gauge is to pick it up by one of its gold wires without bending it. Gently grabbing the wire at its halfway point generally works well. After that, the gauge can be dipped into a puddle of adhesive. The adhesive should have a viscosity that is not too thick or too thin. The right viscosity will fully wet the back of the gauge with a thin layer of adhesive. I found this step to be the trickiest because judging when the back of the gauge touches the adhesive is not obvious. At times, when I try to graze the surface of the adhesive to minimize the amount I pick up, I find that I did not even touch the adhesive when I go to place the gauge. Other times, when I want to make sure I put enough adhesive on the gauge, I go too low into the puddle and end up bending the gold wire. As we'll see in the next sequence, I was only partially successful at getting the right amount of adhesive onto the back of the gauge. The field of view is the same as in the last sequence. It's important to drop the gauge vertically and not at an angle. If done right, the gauge will sit on the surface with its gold wires sticking straight up. The weight of the gold wires will seat the gauge in the adhesive. You can see that the gauge is starting to tip over by the change in the light reflecting off the surface of the gauge. If that happens, the tweezers can be used to tap on the wedge bond to reseat the gauge. We can see that there's too much adhesive on the left side of the gauge in this attempt. Once the adhesive has cured and the solder terminals are installed, the gold wires can be soldered to the solder terminals. The first thing to do is to pre-tin the solder terminals with small solder balls. The second thing to do is to bend and position the gold wires so that they touch one side of the solder ball. It's important that the wires touch the solder ball on their own and that there are no air gaps between the wire and the solder ball. Here we see the gold wires touching their respective solder balls. To successfully solder the gold wires, it's important to supply enough heat to the solder to melt it and not the gold wire. So I'll bring the tip of the soldering iron to the solder ball and just touch it enough to get it to melt. If the wire is touching the solder, it'll get pulled in by the surface tension and embed itself in the solder without melting. The excess gold wire can be pulled off afterwards. I've gone over the 3 installation steps that have given me the most trouble when I try to install a semiconductor strain gauge. I think my success rate is probably somewhere around 50%. Success here means the gauge appears to be properly bonded and is able to solder the gold wires without melting them. This type of installation is good enough for my experiments. Now, if I was prototyping a sensor that would later become a product, I would never rely on my own gauge installations for the verification tests. Instead, I would ask one of our gauging technicians to install the gauges for me, because the data is too important to be corrupted by my poor gauging skills. That would be the counsel that I would give to anyone prototyping a new sensor design that uses semiconductor strain gauges. There's nothing worse than spending a lot of time and money to design a sensor, manufacture it, run it through a series of test sequences, analyze the data, and then realize that the data makes no sense because the gauges have been poorly installed. The Piezo-Metrics gauging technicians have been doing gauging work for a very long time and are very good at it. Having a reliable gauge installation means the data coming from the gauges can be trusted, and therefore any conclusions that are made about the sensor performance can be made with confidence. If you are interested in the Piezo-Metrics gauging services, please contact Piezo-Metrics at the link below.